Voltage, vitality, elevation.
We gaze up at the night sky, filled with wonder and curiosity. Countless stars twinkle back at us, each one beaming its radiance toward Earth, a distant point of light in the vast expanse of space. For millennia, humans have wondered, are we alone in this immense universe? Are there other planets out there, orbiting those distant stars waiting to be discovered? Today we know the answer is a resounding yes. We have found thousands of these distant worlds. We call them exoplanets, planets that exist outside of our own solar system, each one unique and fascinating. They are worlds beyond our cosmic backyard, each with its own story to tell, its own mysteries to unravel. The discovery of exoplanets has revolutionized our understanding of the universe, showing us just how diverse and complex it truly is. It tells us that our solar system, with its familiar planets and moons, is just one tiny part of a much grander cosmic tapestry, a small piece in the vast puzzle of the cosmos. Exoplanets come in all shapes and sizes, from gas giants larger than Jupiter, with their swirling clouds and immense storms, to rocky worlds like our own, with solid surfaces and potential for life. Some orbit close to their stars, basking in intense heat and light, while others are much farther out in the cold, dark reaches of space. The sheer diversity of these alien worlds has ignited our imaginations and fueled our desire to learn more, to explore further, and to understand the universe in ways we never thought possible. For centuries, the existence of exoplanets was purely speculation. The night sky, filled with countless stars, sparked the imagination of many. Ancient philosophers pondered the possibility of other worlds, wondering if those distant points of light could harbor planets like our own. But it wasn't until the 20th century that astronomers began to develop the tools and techniques needed to detect them. The advent of more powerful telescopes and the birth of astrophysics opened new doors. Early attempts focused on observing the gravitational influence of unseen planets on their host stars. These subtle wobbles in a star's position hinted at the presence of orbiting planets. These efforts were challenging, and it wasn't until the late 20th century that the first confirmed discoveries of exoplanets were made. The journey was long and filled with skepticism and hope. In 1992, astronomers announced the discovery of 2 planets orbiting a pulsar, a rapidly rotating neutron star. This was a monumental breakthrough. This discovery, while groundbreaking, was met with some skepticism. The idea of planets surviving in such harsh environments was hard to accept for many. Pulsars are extreme environments, and many scientists questioned whether planets could truly form and survive around such objects. The debate was intense and ongoing. However, just a few years later in 1995, a team of Swiss astronomers made a discovery that would change our view of the universe forever. Their persistence paid off. They found the first confirmed exoplanet orbiting a sun-like star called 51 Pegasi b. Its star, 51 Pegasi, is located about 50 light-years away from Earth in the Pegasus constellation. This discovery opened the floodgates, leading to the identification of thousands of exoplanets in the years that followed. The discovery of 51 Pegasi b sent shockwaves through the scientific community. This was the first time an exoplanet had been found orbiting a star similar to our Sun, and it opened up a whole new realm of possibilities. This discovery earned the discoverers, Michel and Didier, the Nobel Prize in Physics in 2019. 51 Pegasi b is a hot Jupiter, a class of gas giants that closely orbit their parent stars, completing an orbit in just about 4 days. Despite its proximity to its star, leading to scorching surface temperatures estimated to be around 1,000 degrees Celsius, the planet's existence challenged prior theories that gas giants could only form far from their stars similar to Jupiter and Saturn in our solar system, proving that such systems were not just possible, they were likely common throughout the galaxy. The discovery suggested that our solar system was not unique, and that there could be countless other worlds out there waiting to be found. This discovery ushered in a new era of exoplanet hunting, one that continues to this day. With each new discovery, our understanding of the universe grows and our knowledge deepens. Astronomers around the world are now engaged in a race to find more and more exoplanets, using increasingly sophisticated telescopes and techniques. These advancements have allowed us to detect planets that are smaller and farther away than ever before. The ultimate goal of this quest is to find another Earth, a planet that could potentially support life as we know it. Such a discovery would have profound implications for our understanding of life in the universe. To do this, astronomers are searching for planets within the habitable zones of their stars, where temperatures are just right for liquid water to exist on the surface. Liquid water is considered essential for life, making these zones prime targets in the search for habitable planets. They are also looking for planets with atmospheres that could support life, as the presence of an atmosphere can protect a planet's surface and provide the necessary conditions for life to thrive, and for signs of biosignatures, chemical fingerprints that could indicate the presence of living organisms. These biosignatures could be the key to finding life beyond our own planet and are a major focus of current and future exoplanet research. The search for exoplanets has taken us from the realm of speculation to the forefront of scientific discovery. What was once a topic for science fiction has become a vibrant and rapidly evolving field of research. We have learned that our galaxy is teeming with planets, many of which are stranger and more diverse than we ever imagined. And as we continue to explore, we are coming closer to answering one of humanity's oldest and most profound questions. Are we alone? Finding exoplanets is a challenge. They are incredibly small and faint compared to the stars they orbit. It's like trying to spot a firefly next to a blazing spotlight from across a vast, cosmic distance. But astronomers are a clever bunch, and they've developed ingenious methods to overcome these obstacles. These methods rely on indirect detection, observing the effects of exoplanets on their host stars rather than seeing the planets themselves. The transit method is particularly effective at finding planets that orbit relatively close to their stars. This is because the closer a planet is to its star, the more likely it is to transit from our perspective on Earth. Additionally, closer-in planets orbit their stars more quickly, meaning astronomers can observe multiple transits within a shorter time frame, confirming the planet's existence and refining their measurements. The Kepler Space Telescope, launched in 2009, was a game-changer for the transit method. From its unique vantage point in space, Kepler continuously observed a patch of sky containing over 150,000 stars, searching for those telltale dips in brightness. Kepler's mission was a resounding success, discovering thousands of exoplanet candidates and revolutionizing our understanding of planetary systems beyond our own. The amount of light blocked during a transit tells astronomers about the size of the planet. A larger planet will block more light, resulting in a deeper dip. By analyzing the shape and duration of the transit, astronomers can also learn about the planet's orbital period and the shape of its orbit. Combining this information with data about the host star's properties allows astronomers to estimate the planet's temperature and potential habitability. The transit method is a powerful tool for discovering and characterizing exoplanets, but it has its limitations. For a transit to be observable from Earth, the planet's orbit must be perfectly aligned with our line of sight. This means that the transit method is biased towards finding planets in systems that are oriented edge-on to us. Despite this limitation, the transit method has been incredibly successful, accounting for the majority of confirmed exoplanet discoveries to date. Another widely used method for finding exoplanets is the radial velocity method, also known as the Doppler spectroscopy method. This technique relies on the fact that a star and its planets orbit a common center of mass. The gravitational pull of an orbiting planet causes the star to wobble slightly. This wobble is too small to be observed directly, but it can be detected by measuring the Doppler shift of the star's light. As a star moves towards Earth, its light waves are compressed, causing a slight blue shift in its spectrum. Conversely, when a star moves away from Earth, its light waves are stretched, causing a red shift. Astronomers use highly sensitive spectrographs attached to telescopes to measure these minute shifts in a star's spectrum. revealing the presence of an unseen planet tugging on it. The radial velocity method is particularly sensitive to massive planets that orbit close to their stars. These planets exert a stronger gravitational pull on their host stars, resulting in more pronounced wobbles and larger Doppler shifts. By analyzing the pattern of Doppler shifts over time, astronomers can determine the planet's orbital period, mass, and the shape of its orbit. One of the key advantages of the radial velocity method is that it can detect planets regardless of their orbital inclination. Unlike the transit method, which requires a specific alignment, the radial velocity method can find planets even if their orbits are tilted relative to our line of sight. This makes it a valuable tool for studying a wider range of planetary systems. The transit method and the radial velocity method are often used in tandem to confirm the existence of exoplanets and refine our understanding of their properties. For example, if a planet is detected using the transit method, follow-up observations using the radial velocity method can be used to determine its mass. Combining data from both methods provides a more complete picture of the planet and its system. The search for exoplanets is a dynamic and rapidly evolving field. New technologies and techniques are constantly being developed, pushing the boundaries of what we can detect and learn about these distant worlds. As we continue to explore the cosmos, we can expect many more exciting discoveries in the years to come. Each exoplanet discovery adds a new thread to the tapestry of our understanding of the universe. Some discoveries reinforce our existing knowledge, while others challenge our assumptions and force us to rethink what we thought we knew about planetary formation and evolution. The diversity of exoplanets is astounding, showcasing the incredible range of conditions that can exist in the cosmos. From gas giants larger than Jupiter to rocky worlds smaller than Mercury, exoplanets come in all sizes. Some orbit their stars in scorchingly close orbits, completing a year in just a few Earth days, while others take centuries to make a single journey around their star. Some reside in multi-planet systems, engaged in intricate gravitational dances with their siblings, while others are solitary wanderers drifting through the galaxy alone. One of the most surprising early discoveries in exoplanet research was the detection of hot Jupiters. These massive gas giant planets orbit their stars in extremely close proximity, often completing an orbit in just a few days. The discovery of hot Jupiters challenged the traditional model of planetary formation, which suggested that gas giants could only form in the cold, outer regions of a star system. The existence of hot Jupiters suggests that planets can migrate inward after they form, perhaps due to gravitational interactions with their host stars or other planets in their systems. This realization has significant implications for our understanding of how planetary systems evolve and the potential for planets to be ejected from their systems altogether. Another intriguing class of exoplanets is super-Earths. These planets are larger and more massive than Earth, but smaller than Neptune. Super-Earths are of particular interest to astronomers because they represent a type of planet that doesn't exist in our own solar system. Studying these planets provides valuable insights into the diversity of planetary formation and the potential for rocky planets to exist in a wide range of sizes. Some super-Earths are thought to be water worlds, with vast oceans covering their surfaces. Others may have thick atmospheres composed of exotic gases. The composition and habitability of super-Earths depend on a variety of factors, including their distance from their stars, their internal structure, and the presence or absence of an atmosphere. Perhaps the most exciting exoplanet discoveries are those that reside in the habitable zone of their stars. The habitable zone, also known as the Goldilocks zone, is the region around a star where temperatures are just right for liquid water to exist on the surface of a planet. Liquid water is considered essential for life as we know it, so planets in the habitable zone are prime candidates in the search for extraterrestrial life. It's important to note that simply being located in the habitable zone does not guarantee that a planet is habitable. Other factors, such as the planet's atmosphere, its internal activity, and the presence of a protective magnetic field, also play crucial roles. Nevertheless, the discovery of planets in the habitable zone is a tantalizing reminder that the conditions for life may exist on other worlds. One of the most exciting exoplanet discoveries in recent years was the detection of Proxima Centauri b, a planet orbiting Proxima Centauri, the closest star to our Sun. Proxima Centauri b is a rocky planet about 1.3 times the mass of Earth, and it orbits within the habitable zone of its star. The discovery of Proxima Centauri b sent ripples of excitement through the scientific community. Here was a potentially habitable planet orbiting our nearest stellar neighbor, a mere 4.2 light-years away. While much remains unknown about Proxima Centauri b, including its atmosphere and potential for life, its discovery has fueled our imaginations and sparked renewed interest in the search for life beyond Earth. Another remarkable exoplanet system is TRAPPIST-1, a system of 7 Earth-sized planets orbiting an ultra-cool dwarf star about 40 light-years away. What makes TRAPPIST-1 so intriguing is that 3 of its planets reside in the habitable zone, making it the system with the most potentially habitable planets discovered to date. The TRAPPIST-1 planets are so close to each other that they would appear prominently in each other's skies, much larger than our moon appears to us. While the TRAPPIST-1 system presents challenges for life as we know it, including the fact that the planets are likely tidally locked to their star, its discovery highlights the incredible diversity of planetary systems that exist in our galaxy. These discoveries are just the tip of the iceberg. With each new generation of telescopes and instruments, we are discovering more and more exoplanets, each one with its own uniqueness. The quest to find other Earths, planets that could potentially harbor life, continues to drive exoplanet research, inspiring us to explore the cosmos and unravel the mysteries of the universe. Leading the charge in this new era of exoplanet exploration is the James Webb Space Telescope, the largest and most powerful space telescope ever built. Launched on Christmas Day, December 25, 2021, the JWST promises to revolutionize our understanding of the universe, including the study of exoplanets. With its massive gold-coated mirror and advanced suite of instruments, the JWST can observe the universe in infrared light with unprecedented sensitivity and resolution. This capability is crucial for studying exoplanets because it allows astronomers to see through the dust and gas that often obscure young planetary systems. One of the JWST's primary objectives is to study the atmospheres of exoplanets, searching for clues about their composition, temperature, and potential for habitability. When an exoplanet passes in front of its star, some of the starlight filters through the planet's atmosphere. By analyzing this filtered light, astronomers can identify the chemical fingerprints of different molecules in the atmosphere. The JWST's sensitive transit spectroscopy capabilities allow astronomers to determine the presence of water vapor, methane, carbon dioxide, and other molecules that could indicate the presence of a habitable environment. The JWST's sensitivity and resolution will enable it to study the atmospheres of smaller, cooler planets than ever before, including those that may be similar to Earth. Beyond identifying the basic building blocks of life, the JWST will also search for signs of life itself, known as biosignatures. Biosignatures are chemical or physical markers that could indicate the presence of living organisms on an exoplanet. Examples of biosignatures include the presence of oxygen and methane together in an atmosphere, which could indicate biological activity, or the detection of complex organic molecules that are not easily explained by abiotic processes. While the detection of biosignatures would not definitively prove the existence of extraterrestrial life, it would be a significant step towards answering the question of whether we are alone in the universe. While space-based telescopes like the JWST offer unparalleled views of the cosmos, ground-based observatories continue to play a vital role in exoplanet research. New generations of ground-based telescopes are being built with larger mirrors, advanced adaptive optics systems, and sophisticated instruments designed specifically for exoplanet hunting. These ground-based giants will complement the capabilities of space-based observatories, providing high-resolution imaging, precise spectroscopic measurements, and long-term monitoring of exoplanet systems. They will be particularly adept at discovering and characterizing planets around nearby stars, which are brighter and easier to study from Earth. The future of exoplanet research is bright. fueled by technological advancements, innovative observational techniques, and an unyielding desire to explore the unknown. As we peer deeper into the realm of exoplanetary systems, we can expect to uncover a universe of possibilities, challenging our assumptions, expanding our understanding of planetary formation and evolution, and perhaps even revealing the existence of life beyond Earth. Each new discovery brings us one step closer to unraveling the mysteries of these distant worlds and answering the fundamental questions that have captivated humanity for centuries. The hunt for exoplanets is a journey of exploration, discovery, and the pursuit of knowledge that will continue to inspire generations to come. The discovery of exoplanets has fundamentally changed our perspective on the universe. We once thought our solar system, with its familiar planets and moons, was unique. Now we know that planets are not the exception but the rule in the cosmos. Our galaxy, the Milky Way, is teeming with billions upon billions of planets, each a world unto itself. This realization is both humbling and awe-inspiring. It tells us that our place in the universe is not privileged, but rather one of countless possibilities. The sheer diversity of exoplanets we've discovered, from hot Jupiters to super-Earths, from water worlds to planets orbiting pulsars, has shattered our preconceived notions and opened our minds to a universe far stranger and more wonderful than we could have imagined. The study of exoplanets is not just about cataloging celestial objects, it's about understanding the conditions necessary for life to arise. By studying the atmospheres of exoplanets, we can learn about their composition, temperature, and potential habitability. We can search for the presence of water, methane, carbon dioxide, and other molecules that are essential for life as we know it. The discovery of planets in the habitable zones of other stars, where conditions might be just right for liquid water to exist on their surfaces, fuels our hope that we may not be alone in the universe. While we have yet to find definitive proof of extraterrestrial life, the search itself is a testament to our innate curiosity and our desire to understand our place in the grand scheme of things. The ultimate goal of exoplanet research is to find another Earth, a planet so similar to our own that it could support life as we know it. This is a daunting task, as Earth-like planets are likely to be small, faint, and difficult to detect across the vast distances of space. However, new generations of telescopes and instruments are being developed that will be capable of detecting and characterizing Earth-sized planets around other stars. These instruments will use advanced techniques to block out the blinding light of stars, allowing us to see the faint glow of planets orbiting them. With each technological leap, we come closer to answering the age-old question: is there another Earth somewhere out there? Beyond the search for life, the study of exoplanets has revealed a universe of wonder and diversity beyond our wildest dreams. We've discovered planets orbiting two stars like something out of Star Wars. We've found planets that are denser than lead and others that are lighter than air. We've even detected planets around pulsars, the remnants of exploded stars. These discoveries have challenged our understanding of how planets form and evolve. They've shown us that our own solar system, once thought to be the blueprint for planetary systems, is just one of countless variations on a theme. The universe is a far more imaginative artist than we could have ever imagined. The study of exoplanets is ultimately a journey of self-discovery. As we learn about these distant worlds, we gain a deeper appreciation for the uniqueness and fragility of our own planet. We begin to see Earth not as an isolated island, but as a precious oasis in the vastness of space. The discovery of exoplanets has ignited our imaginations and inspired us to dream of a future where we might one day travel to these distant worlds. While such journeys may be a long way off, the knowledge we gain from studying exoplanets today will undoubtedly shape our understanding of the universe for generations to come. What do you think about the study of exoplanets? Do you feel that the JWST will find an exoplanet that exhibits technosignatures or the signs of biological life in the atmosphere of a distant planet? Do you think we'll find another planet like the Earth that orbits a star similar to our own, rich with life and maybe even a civilization? The thought that we may not be alone is both exciting and also a little frightening. Will the James Webb Space Telescope accomplish its goal of finding another Earth-like planet, somewhere out there rich with geological features, life, and diversity? a sister planet or twin to the Earth. The universe is full of possibilities and surprises. Who knows what the universe holds for us, and what we will find in its vastness? I guess only time will tell, as we continue to scan the stars for habitable exoplanets and search for signs of life in the expanse of the cosmos. Thank you so much for watching. Please like and subscribe to show your support for the channel. Stay tuned, folks, there is much more to come. Until next time, guys, always stay elevated. Cheers.
Thanks for watching Voltage Vitality Elevation. Please select one of the videos displayed on the screen to continue watching.